Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
What if the most dangerous thing in your cockpit isn't a sudden engine failure or, a freak microburst or a flock of birds? What if it's actually the glowing magenta line on your multi-$1,000 flight display?
Yeah, it's a pretty jarring thought, isn't it? I mean, we are just so conditioned to view technology as our ultimate safety net.
Right, like it's there to save us.
Exactly. But when you look at the human factors involved in modern aviation, that beautiful, perfectly calibrated screen can actually become this really subtle trap.
Which is exactly why we're diving into this today. Welcome to Deep Dive. I'm your host. And if you are sitting there right now listening to this, maybe working towards your private pilot license, learning to fly is a very visceral experience for you.
Oh, absolutely. And I'm just thrilled to be here to break this down with you today because, for student pilot, you picture your hands gripping the yoke, your feet dancing on the rudder pedals, you're feeling the wind push back against the control surfaces.
Yeah, the actual feeling of flying. But the reality of the technically advanced aircraft like the TAA you might be training in right now, it looks a little different. So, okay, let's unpack this. Today, we're taking a massive stack of aviation research, simulator data, and accident reports to understand how modern glass cockpits are completely changing the way pilots fly.
And sometimes how they forget to fly.
Right. We're talking about primary flight displays, multifunction flight displays, all those glowing screens that are replacing the old school mechanical dials.
And to be fair to the engineers who designed all this automation is arguably the single most important advance in aviation history. I mean, it has completely revolutionized the flight deck.
Oh, sure.
You no longer have a cockpit that's just cluttered with a huge library of handbooks and performance charts. Instead, you've got these sleek electronic databases.
Yeah, and incredible moving maps, right? Like maps that mirror your VFR sectional charts right alongside real-time traffic and terrain graphics.
Yeah.
It's an astonishing amount of capability just sitting right at your fingertips.
It really is. It reduces incredibly complex navigation down to just, a visual line on a map.
I mean, who wouldn't want all that data? It sounds like cheating, but in the best way possible. But digging into the research on the table today, a much more unsettling theme emerges. Mastering a modern aircraft isn't just about rudder pedals and ailerons anymore.
No, not at all.
It's about not letting a brilliantly designed computer lull you into a false sense of security.
Yeah, because the double-edged sword, the electronic flight display makes certain navigational errors way more evident, sure, but they actually hide other more fundamental errors.
Right.
Or they change the pilot's behavior so drastically that the human being introduces entirely new risks into the flight path.
So let's look at the real-world consequences of that, starting with this pivotal study by the British Airline Pilots Association.
Yeah.
They issued a surprisingly blunt warning to the industry.
They really did.
They officially stated that pilots were increasingly lacking basic flying skills as a direct result of relying on automation. And they weren't just guessing, right?
No, they backed this up with a massive simulator study. They basically compared two very distinct groups of twin-jet airliner crews. It was sort of the perfect laboratory setup to isolate the variable of the screen itself.
Okay, walk us through that setup.
So you had a control group flying an older analog-equipped version of an aircraft, the classic six-pack of mechanical dials and gauges.
Classic raw data.
Exactly. And then you had an experimental group flying the exact same aerodynamic model, but equipped with a modern electronic flight instrument system, or EFIS, complete with a super robust flight management system.
Okay.
And they threw just everything at both groups during these 4-hour simulator sessions. Normal maneuvers, abnormal maneuvers, full-blown emergencies.
Let me guess. The guys with the mechanical dials just pointed the nose down and flew the plane based on feeling, while the EFIS guys started, playing IT technician.
That is precisely what happened, and honestly, it started even before the emergencies.
Wait, really? Just during normal flight?
Yeah, just during normal maneuvers, like basic things, turning to a heading without the autopilot's flight director superimposed on the screen to tell them exactly where to point the nose. The EFIS group exhibited way greater deviations.
Wow.
They definitively struggled to stay on the localizer and the glide slope as smoothly as the analog crews did.
Just to clarify, for anyone newer to instrument concepts listening right now, when we say localizer and glide slope, We're talking about those invisible, highly precise radio beams guiding you down to the runway, right? Keeping you aligned horizontally and vertically.
Correct. And to be clear, the EFIS pilots stayed within the legal practical test standards, so they didn't fail.
Oh, okay. But it was sloppy.
Yeah, their actual physical aircraft control was noticeably degraded. There was documentable erosion of basic hand-flying proficiency.
It almost feels counterintuitive, doesn't it? You'd assume the pilots with the multi-million-dollar processing power would perform better under pressure. But it honestly reminds me of driving a car today.
Oh, the GPS analogy.
Yeah. You see people who are so completely reliant on the GPS app on their phone that if it suddenly loses signal, they realize they have absolutely no idea how to navigate their own neighborhood. They've completely outsourced their internal sense of direction to a machine.
And that outsourcing mechanism is identical in the cockpit. And the danger of outsourcing those foundational skills became glaringly obvious in the simulator study when the researchers introduced an abnormal maneuver.
The slam dunk descent.
Yes.
The slam dunk descent.
Put us in the left seat for a second. What does a slam dunk descent actually demand of a pilot physically and mentally?
Imagine you are cruising at a high altitude, and air traffic control suddenly gives you a very close crossing restriction. They say, cross 10 miles south of the VOR at 3,000 feet.
Okay, so you have to drop a ton of altitude fast.
Right. You have to drop a massive amount of altitude quickly and hit a very specific point in space. It requires rapid spatial calculation, energy management, and decisive physical control of the aircraft.
So the analog crews, the ones used to raw data, how did their brains process that sudden demand? They utilized basic mental math, usually called the 3-to-1 rule. They use it to visualize the descent profile in their heads, and then they simply executed it.
It just flew the plane.
They physically pitched the nose down, pulled the power back, actively managed their airspeed, and smoothly maneuvered the aircraft to make the restriction. They remained looking out the window or scanning their raw instruments. Their situational awareness remained incredibly broad.
And the EFIS crews, you mentioned they turned into IT technicians. Did they experience what psychologists call cognitive tunneling?
Oh, very much so. Under the sudden pressure of task saturation, the EFIS crews tended to go completely heads down.
Just staring at their last.
Exactly. Instead of managing pitch and power, their immediate instinct was to command the computer to solve the problem for them. They furiously tried to program the new crossing restriction into their flight management system, diving through all these submenus to build a vertical navigation profile.
So they're basically trying to type their way out of a dynamic, real-world physical situation.
Which eats up an incredible amount of cognitive bandwidth. And the same phenomenon occurred when they were assigned a sudden runway change on short final approach.
Oh, wow. Close to the ground.
Very close. The analog crews mentally transitioned, manually captured the new parallel runway's localizer, and just flew the approach. The EFIS crews spent a significant amount of critical time with their heads buried in the screens, trying to reprogram the approach into the computer while flying dangerously close to the ground.
That is a huge takeaway for you as a student pilot listening to this. If you're coming in for a landing and ATC changes your runway, your instinct shouldn't be to stare down at your lap and start frantically twisting knobs.
Right.
What the data shows is that task saturation forces an erratic and dangerous eye scan.
Right, the eye scan just falls apart.
So sometimes the absolute best option is to just disengage the automated system entirely. Turn off the flight director, look up, and just hand fly the airplane.
And the simulator data backs that up emphatically. When the EFIS crews had their flight directors intentionally disabled during an emergency like an engine failure, their manual flying severely deteriorated.
Because they were looking for the magenta line.
Yes. Their eye scan became this erratic searching pattern. They were subconsciously looking for the computer to give them a command rather than just reading the raw data of the aircraft's physical performance.
Okay, so if task saturation is what causes pilots to bury their heads in the screen during a critical phase of flight, how do we actually train our brains to look up? Like, is it just sheer willpower? Because this automation is here to stay.
Mm-hmm.
So how does a student pilot safely manage all these systems without becoming completely dependent on them?
It really requires a fundamental shift in how you view the avionics themselves. The literature breaks this down into 3 necessary pillars of mastery: information management, automation management, and risk management.
Okay.
And it starts with moving past what flight instructors call rote workmanship.
Meaning just memorizing a sequence of button pushes without actually understanding the underlying logic of the system.
Exactly that. If you are sitting in the cockpit and you have to pause and analyze, okay, which knob do I twist next to get this page? Or if you blindly follow the exact same sequence of keystrokes every single time just because that's how your instructor showed you once, your working memory is doing all the heavy lifting.
And working memory is terrible under stress.
Right. Under stress, your working memory gets completely overloaded and you just freeze. True mental mastery means comprehending the system's architecture so well that when a situation gets dynamic, you know how to make the system work for you. You aren't just serving as an administrative assistant to the computer.
Now, here's where it gets really interesting. To achieve that level of mastery, the research suggests a strategy that actually feels completely counterintuitive when you're dealing with modern tech. It's the stop, look, and read strategy.
It's so vital.
Because when I first read that, I thought of how people interact with their smartphones, right? The instinct is to just start tapping immediately to make the screen do what you want.
Oh, yeah. And pilots new to advanced avionics do the exact same thing. They become totally fixated on the physical action of turning knobs, but the stop, look, and read protocol forces a pause.
You physically stop.
You stop your hands, you look at the display, and you literally read what the system is currently telling you before you input a single command.
That makes so much sense.
Reading before you twist a dial prevents you from commanding the automation to do something it's already doing, or worse, fighting against a mode it's currently locked into.
I imagine it's also about managing just the sheer volume of data. It feels a bit like trying to find a crucial Post-it note on a desk that is completely buried in textbooks and old coffee cups. You don't need every piece of information screaming at you all the time.
That desk analogy is perfect for information management. You have to actively meter and prioritize the flow of data. You have to declutter the screen.
So practically speaking, what does that look like?
Well, if you are flying en route, straight and level at altitude, your map scale should be dialed way out to give you the big picture of weather systems and restricted airspace.
Right.
But when you enter the terminal area to land, having a map scaled to 200 miles is totally useless. You need to scale that map in tight. If you are flying at night or in the clouds near mountains, you need to pull up that specific terrain awareness page.
So you configure the screens to give you exactly what you need for that specific phase of flight and just strip away everything else.
Precisely.
Okay, so decluttering the screen handles information management. But let's get into the mechanics of automation management. Because we constantly hear stories of the computer doing things we don't expect.
Yeah.
How exactly do these systems trick a pilot if they aren't paying close attention?
Well, the systems trick pilots because computers lack common sense. They only follow their immediate programming logic. A really classic example of this from the sources is the ROL mode trap. ROL mode.
Okay, break that down for us.
Let's say you have your autopilot engaged, and it's in NAV mode, meaning it is actively tracking a GPS course you've programmed. The plane is perfectly tracking the magenta line for you.
Everything is smooth, you're enjoying the view.
Exactly. Now, let's say you reach a point in the flight where you decide to change your navigation source on your electronic display. You switch it from the GPS satellite data over to a local VOR station, a ground-based radio signal.
Which is a completely normal procedure.
It is entirely normal. But depending on the specific avionics suite you're flying, the moment you change that navigation source, the autopilot might automatically drop its NAV tracking mode entirely.
Just drop it without asking.
Yep, because the logic of the computer says, well, the GPS source I was following just disappeared. Therefore, I will default to my most basic lateral control mode. And that default is known as RL mode, or wing level mode.
Oh, I see the trap. The autopilot hasn't turned off.
Nope.
It's still actively flying the plane, keeping the wings perfectly flat, but it is no longer turning to follow your intended course. It's literally just flying straight ahead into whatever's in front of you.
Yes. And if you don't catch that subtle green text change at the top of your primary flight display, the mode enunciator switching from NAV to ROL, you are going to deviate miles off your course, all while assuming the computer is still navigating for you.
Because the plane feels completely stable.
The plane feels fine, the screens are all glowing happily, but you are creating a massive navigational error.
That is incredibly insidious, which explains why the training manuals we read are absolutely adamant about using verbal callouts to manage automation.
Verbal callouts are essential, even if you are flying solo as a student pilot. I know it might feel ridiculous at first, just talking to yourself in an empty cockpit.
Totally.
But physically speaking, the words, saying out loud, navigation source switch to VOR, autopilot NAV mode re-engaged, it serves as a neurological override.
It snaps you out of it.
It breaks the trance of staring at a screen. It forces your brain to consciously process the state of the automation.
And that physical override is so important because it moves us into the ultimate escalation of this issue, which is risk management. We aren't just talking about busting a check ride here or, embarrassing yourself in front of an instructor. We're talking about the fatal consequences of failing to monitor these systems properly.
Right. And to understand why these fatal accidents happen, we really have to confront a deeply ingrained physiological limitation. It's heavily documented in the research as the paradox of automation, driven by something called the vigilance decrement.
The idea that human beings are characteristically terrible at passively monitoring highly reliable systems.
We really are. We are evolutionary built for action and movement. We are not built for staring at a perfectly functioning machine waiting for a 1 in 1,000 error.
Yeah, our brains just get bored.
When an automated system works flawlessly 99% of the time, our brains naturally tune it out to save energy. We subconsciously stop verifying its work. The more reliable the system, the poorer the human performance in monitoring it.
That dynamic is terrifying. The computer is so good that you stop double-checking it. And when you stop double-checking it, your situational awareness just drops to zero. That actually brings us to a highly studied 1999 aircraft accident in the Andes Mountains.
Yeah.
Walk us through the mechanics of what went wrong there because it perfectly illustrates this paradox.
It's a very sobering case study in automation reliance. So, a multi-engine aircraft crewed by 2 professional pilots was flying a route in Colombia.
Really?
They were heavily utilizing their flight management system.
Okay.
While programming their route into the computer before departure, they made a tiny, almost imperceptible data entry error. They entered a single waypoint incorrectly by just 1 degree.
1 degree. That seems so minor when you're just tapping away at a keypad.
It does. But over distance, that 1 degree of lateral divergence compounded massively. The computer accepted the input without question, and once airborne, the autopilot dutifully began flying the course it was programmed to fly.
Doing its job.
Exactly. And because the plane was flying smoothly, the pilots succumbed to the vigilance decrement. They tuned out. The aircraft flew them 60 nautical miles completely off their intended route.
But surely they had other navigational tools to cross-reference. I mean, how does a professional crew not notice they are 60 miles off course?
That is where the psychology of cognitive offloading and confirmation bias becomes fatal. They had all the raw data right in front of them. The proper paper charts were physically in the cockpit with them.
Wow.
Their correct route was posted on those charts. They even had a paper navigation log indicating the proper heading for every single leg of the flight.
So they outsourced their situational awareness to the screen, and their brains just discarded the contradictory paper data sitting right in their laps.
Exactly. Confirmation bias made them implicitly trust the glowing screen over their analog tools. They allowed the computer to manage itself. The system did exactly what it was programmed to do based on that 1 degree error.
Which was?
It flew a perfectly stable, perfectly automated course directly into the face of a mountain, resulting in multiple fatalities.
So what does this all mean? They had the tools, but their minds were no longer actively flying the airplane. The investigation reports use a very specific, chilling phrase for this phenomenon. They state that the pilots became detached from the operation of the aircraft, sliding into the complacent role of passenger in command.
Passenger in command. It perfectly captures the danger. You're sitting in the left seat, you are legally the pilot in command, but mentally you are just along for the ride.
Which is wild to think about.
It is. And for a student pilot, the crucial lesson here is that advanced avionics do not compensate for a lack of aeronautical skill, and they certainly cannot replace aeronautical decision-making or ADM. The gadgets are tools. Your brain is the primary instrument.
Which brings us full circle. An electronic flight display is an incredible piece of technology. It adds immense quality, precision, and situational awareness to your flight experience. But it is never a substitute for basic airmanship.
Yeah.
At no time is that moving map meant to completely substitute for your ability to read a physical VFR sectional chart or, just look out the window to identify a landmark.
No, absolutely not. The golden rule drawn from all this human factors research is simple. You must intentionally practice manual flying.
Just turn it off.
Yes.
Yeah.
Occasionally, deliberately disengage the automation. Turn off the autopilot. Turn off the flight director. Manually fly the aircraft using raw data. Force yourself to do the mental math. Keep your physical stick and rudder proficiency razor sharp because you will eventually need it.
You will need it because, at the end of the day, a staggering 40% of all general aviation accidents happen during the landing phase. Another 15% occur during takeoff and initial climb.
Right. And those are dynamic, sensory-heavy phases of flight that, in a light GA aircraft, still cannot be outsourced to a microchip. A computer cannot feel the subtle shift of a crosswind on short final.
No.
A machine cannot feel the seat of the pants need to apply the exact right amount of right rudder during your initial climb out to stay coordinated. You have to fly the airplane.
It's all about finding that elusive balance, embracing the incredible capabilities of the technology, but maintaining a healthy, constant skepticism of it. Which leaves you with a final thought to ponder next time you're doing your pre-flight checks and watching those big screens boot up.
Yeah.
We've established the paradox of automation.
As avionics get more and more reliable, human beings become physiologically worse and worse at monitoring them. So in our relentless, industry-wide pursuit of the perfectly automated airplane, will the most dangerous component in the cockpit ultimately become the human brain sitting in the left seat?
It certainly challenges every assumption we have about what it means to truly be in control of a machine. It really does. Learning to fly isn't just about the physical feeling of the rudder pedals anymore. It's about keeping your mind actively engaged in the flight, fighting off complacency, and making sure that when the screens go dark or the computer confidently lies to you, you still know exactly how to fly the airplane.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.